In this video, I'll be talking about state space representation of linear time invariant systems. We will be using state space representation in robust control. And it's important to point out some important properties of that. So you should have studied these in an earlier course. So what you're going to see in this video is just a quick review of some important aspects. Okay, so let's just start with the model itself. So the state space model for a linear time invariant system will be in this form. So this is one of the nicest things about this model actually. So you have this vector first order differential equation, and any LTI system you can imagine will fit into this form. So your system may be just a very simple system with 1 degree of freedom, or it may be very complicated with many degrees of freedom, many inertial elements moving together. So what will change is as the dynamics get more complicated, the order of the state vector will be growing. So this state vector can be just a scalar, as just a single variable, or it may contain tens or even hundreds of variables in the case of a very complicated system. Likewise, if you have a scalar input, then your U signal will be just a scalar signal, and that will make the B matrix a column matrix. But as more inputs are added to the system, what we'll do is it will just make this U a vector signal, and the B matrix will be getting columns corresponding to each input. Likewise, in the output equation, if you have just single output, then Y will be scalar and C will be a row vector. But as additional outputs are introduced, your C and D matrices will be getting additional rows. But this form of the equation is the same, no matter what the system you're working on. And only the dimensions of these matrices and their numerical values obviously will be changing. Good. So whenever you have a state space system, you can obtain the solution in time domain, and that becomes quite handy when proving some of the theorems. So we should just remember that and see how that solution is obtained. So we start by this equation, and our goal is to obtain a solution to that. So we just employ a trick that we do in solving differential equations. We get that equation and multiply that entire equation from left with this matrix. So when you do that, you can, the details are seen here, these two terms can be combined. And when you look at that, you can see that it is nothing but this derivative term opened using the chain rule. So once you recognize that, you can make that equation and take the integral of it. On the left hand side, you have the integral of that term, and on the right hand side, this is the integral you have. So that term on the left can be opened as that. So the integration limits are assuming that this initial time is 0, and you integrate it up to time t. On the left hand side, you have that, and the right hand side, the integral is still the same. Now you multiply this entire equation with e to power at, and that will bring the equation into that form. Okay, so this is the solution of that state space model in time domain. And in fact, in that expression, we define what is called a state transition matrix. So this term is an n by n matrix, and that's known as the state transition matrix. And by using that, the solution in time domain turns into this expression. And that state transition matrix can be written as a summation. So this comes from the Taylor series, so normally you have an infinite sum. However, as we will later see, the Cayley-Hamilton theorem says that the orders of the matrix A higher than the order of the matrix itself can be written in terms of the lower order terms. So that theorem makes this summation a finite summation. Okay, so we will be using this state transition matrix as well. We will not be purely working in state space model. we will be switching back and forth with the transfer function model because we want to make use of these nice tools available in classical control. So in that regard, it's important to know the relation between a state space model and a transfer function. They, in the end, represent the same system. So the transfer function is a complex function defined in S domain, and state space is a model in time domain, and they represent the same system, and obviously they are related. So you should be able to switch back and forth between a transfer function and a state space model. Now let's take a look at how we can obtain the transfer function corresponding to a state space model. So we do that by taking the Laplace transform of our state equations with zero initial conditions, obviously, as we always do when obtaining transfer functions. This is what we have for the state equation, and we can combine the x terms, and since these are matrices, x is a vector and A is a matrix, to combine this into parentheses, you need to insert the identity matrix here so that this is dimensionally compatible. And you combine them on the left hand side and you multiply the matrix with the inverse of Si minus A, and this gives you the x state vector, the Laplace transform of the state vector. Next, we insert that into our output equation, and this will give the relation we're looking for. The Laplace transform of the output is equal to this term times the Laplace transform of the input, which means the term we have in parentheses is our transfer function. So this is the transfer function that corresponds to the state space model with matrices A, B, C, and D. Transfer function of a linear time invariant system is a complex rational function, which means it is a polynomial function of S, complex variable S, divided by another polynomial function of S, which was shown earlier in equation 5. Let's see if we can jump to that equation and then come back quickly. Okay, so it looks like the link is broken here. Anyway, so you know what the transfer function looks like. If you have a multiple input, multiple output system, in that case, the transfer function becomes a matrix. So if your system has P inputs, then the transfer function will have P columns corresponding to that. And if you have Q outputs, and the number of rows of the transfer function will be Q. And you have a scalar transfer function between every input and every output. So when you look at the element of the transfer function matrix at the ith row and jth column, that transfer function is a scalar transfer function, and it is the transfer function between the jth input and the ith output. So your transfer function matrix is a giant matrix where every element is a transfer function itself. For a multiple input, multiple output system with P inputs and Q outputs, it's easy to see that this expression you see in equation 6 indeed gives you a matrix of proper order. C is a matrix with Q rows and N columns. Si minus A has the same dimensions as A, which is n by n. And B is a matrix with n rows and P columns. So when you perform they're compatible. First of all, they can be multiplied. They have proper orders. And what you'll get in the end will be a matrix with Q rows and P columns. So this indeed gives you the transfer function matrix of correct order for your MIMO system. I'm sure you have all seen this expression before, that relates the state space matrix to the transfer function. But I want you to think a little bit about that, and I want to show some important facts about that equation. Well, first of all, the transfer function is a function of S. So these are all constant matrices, just numerical matrices. And the only S term here is this one here. So the entire S variable in transfer function comes from this inverse matrix. So you need to look into that to understand how the matrix A is related to the transfer function. So let's come here. You need to take the inverse of this square n by n matrix, which is a function of S. And the inverse of a large matrix can be written in terms of this. So you must have seen this from your earlier math courses. So you have the adjunct or adjoint matrix of Si minus A, and you divide it by the determinant of that matrix, Si minus A. Now, determinant is a scalar, so you can perform this division. So determinant, if this was a matrix, then obviously you wouldn't be able to write it in the form of division. It would have to be an inverse matrix. But since this is a determinant, it's perfectly fine to write it as a division. So the adjunct gives you an n by n matrix, and this matrix will have elements of variable S. And then you divide each of these elements with the determinant of Si minus A. So the numerator polynomials in transfer function matrix come from the adjunct matrix, and the denominator polynomial comes from this determinant Si minus A, which is a scalar polynomial of order n. Therefore, we can say that all the Q times P transfer functions in the transfer function matrix share the same denominator. So the numerators are different depending on each element of this adjunct matrix, but each one of those terms is divided by the determinant Si minus A. So the transfer function is composed of numerator polynomial of S divided by denominator polynomial S. And the denominator polynomial of a transfer function is called the characteristic polynomial of the system. And when you take that denominator of S and equate it to 0, this becomes an equation. And that equation is called the characteristic polynomial. So when you come to this relation, the denominator polynomial for the entire transfer function matrix is the determinant of Si minus A, and this is the characteristic equation for the transfer function matrix you obtained from the state space model. The characteristic equation of a system is an nth order polynomial, and we know that an nth order polynomial has n poles, n roots, and we call these roots the poles of the system. And these poles may be real numbers or complex numbers, depending on the coefficients of the polynomial. However, if there's a complex root, then the conjugate of that complex root will also be a root at the same time. And this is because of the fact that this polynomial has real coefficients. Okay. Now, this equation should also look familiar from the definition of an eigenvalue. Any value of S that satisfies this equation is called an eigenvalue of the matrix A. And any value of S that satisfies this equation is also a root of the polynomial. So from here we conclude that the poles of a system, or the poles of a transfer function of a system, are equal to the eigenvalues of the system matrix A when you write that system in state space form. So this is actually an important fact. Well, I'm sure this is really not new to any one of you, but perhaps you never thought about this equality of the eigenvalues of the matrix and the poles of the transfer function. They are in fact the same thing. So when you have a transfer function, you can analyze its stability by checking its poles. You know that all the poles should have negative real parts for stability. And if you have the state space model, you do the same thing on the eigenvalues of matrix A. So you don't have to go back to transfer function and find out the poles to check stability. You can just do it right in the state space model by checking the eigenvalues of matrix A. And there's another important fact here that I should mention. So in a multi-input, multi-output system, you have a transfer function matrix. And every transfer function in matrix may have different numerator polynomials, but the denominator polynomial is the same for each and every one of transfer functions in the transfer function matrix, which means for a MIME system with dimensions Q and P, there are different numerators, but there's only one characteristic equation for a multi-input, multi-output system. And that equation is given by that. When switching back and forth between state space model and transfer function, we will use this shorthand notation. So whenever you see a matrix like that with A, B, C, and you can have D here, and you see these partition lines, this indicates that this is in fact a transfer function matrix. So this is equal to that expression we had above, Si minus A inverse times B plus D. Okay, so do not confuse this with a constant matrix, a constant numerical matrix that you can obtain by stacking A, B, C, D matrix into a single matrix, which you can do because these are dimensionally compatible. Rather, this notation will give you a function of S, transfer function matrix of S. Okay, a very important property of state space model is that it's not unique. In fact, you can have infinitely many state space models for the very same system. So each model will have a different state vector definition, but the inputs and outputs are the input and output of the physical system, and they are the same, but the internal, the state vector will be changing for these state space models. And you can switch from one state space model to another using what's called a similarity transformation. So let's remember how you do that. Suppose that you have an original state space model with state vector x and corresponding A, B, C, D matrices. You pick any invertible n by n square matrix T, and this could be literally anything. And since you can define infinitely many invertible n by n transformation matrices, you can have infinitely many state space models. And let's see how we can obtain the state space model corresponding to this transformation matrix. So you take that invertible matrix and multiply your original state vector with that, and what you get will be your new state variable z. And since this is invertible, you can express the original state vector in terms of new state vector through this relation. You multiply it with the inverse of t. Next, let's write the state equation for the new variable. You take the derivative of that. Since t is a constant matrix, the derivative will give you t times the derivative of x. And for derivative of x, you insert the state equation from the original state space model. Then you replace the original state vector x with the new state vector as you defined here. And that will bring the state space state equation for the new state variable into that form. You go back to the output equation, the original output equation, and you replace the original state vector with the new state vector, and that will give you the output equation for the new state variable. So when you put them together, this becomes the state matrix, system matrix for the new model. So that's your new state system matrix. This is the new input matrix for the new state space model. This is the new input matrix. The output matrix is also changed. So this is the new output matrix. And the matrix that gives the pass-through term between the input u and the output y directly doesn't change because the input and output variables are the same. So in the new model, the new D matrix is the same as the old D matrix. So this is how you can write a state space model in terms of a different state variable. And this represents the same system as we will see now. Now we have two different state space models with matrices A, B, C, D and matrices A bar, B bar, C bar, and D bar. So do we still represent the same system, or did we obtain a model for a completely different system? Did we change the dynamics of the system? Well, to find the answer, let's check the transfer functions corresponding to these two different state space representations. So we have two transfer functions with these two set of state space matrices. Let's write the transfer function for each one and see if they are equal or not. So for the first one, the transfer function matrix is expressed here. For the second one, I write the same expression with the matrices of the new model, and then I replace the matrix of the new model with these terms which relate them with the original matrices. Okay, now the question becomes, are these two equal to each other? Well, to see if this is equal to this one or not, let me point out a mathematical fact. The inverse of this matrix, you multiply t by si minus a times t inverse. So you take this product of matrices and take the inverse. And I'm saying that that is equal to this expression. T times, you take the inverse of this middle matrix, si minus a inverse, and then you multiply it with t inverse. And I can prove that this is in fact true. So this is how you can show that this fact is correct. Well, first assume that it is indeed correct. If it is correct, then multiplying this inverse with the matrix itself should produce the identity matrix. Okay, so that's what I'm going to do here. The matrix inside is put here, and for the inverse, I write that here. Okay, so this is, we're claiming that is equal to that. Okay, so we put there, and once you put it, you see some obvious simplifications. In the middle, you have t inverse multiplies t. So this gives the identity matrix, so you can just get rid of that. And when you remove that term from the middle, now these two terms come next to each other. The inverse of si minus a multiplies si minus a itself, which produces another identity matrix. So you get rid of this term in the middle, and at the last step, you're left with t times t inverse, which is obviously identity. So if you assume this identity, you can easily show that that identity satisfies identity is equal to identity, so which proves that the fact we wrote here is correct. Okay, so now using this fact, we go back to the expression for GZ, and instead of this term, well, using that identity, you bring it into this form, and you see these cancellations here. These cancel each other out, and you are left with the expression that is exactly the same as the transfer function expression for the original state space model. And this proves that when you perform a similarity transformation, you obtain different ABCD matrices. However, it still has the same transfer function as the original system, and which means that the similarity transformation doesn't change the dynamics, and it still represents the same system. And obviously this is independent of matrix T. So what the matrix T is irrelevant here. For any valid invertible T matrix, this will be valid. And all of the infinitely many state space models you can write for the same system will have the same transfer function, and that means it will represent, they all will all represent the same system. Well, I just noticed that I think I missed a step here, so let me just complete that so that, well, it is quite straightforward, but still I don't like missing steps. So let me just go back here and then fix that. Okay, so let me start from here. Oops, let me just try it one more time. Well, I think that's good enough. Okay, so I have identity matrix here. I can write identity as T times T inverse minus T times A times T inverse. And then there's inverse of this entire thing. And I can write, take this term inside the parentheses into T parentheses from left and T inverse parentheses from the right. So that will give me T parentheses S times identity minus A. Right, on the right I will have T inverse, now the inverse of everything. Okay, now this is what I have in the fact. Okay, so now I can use replace that term with this one, and then the proof follows from there. Okay, so this fact that state space models are infinitely many bring great flexibility. So unlike transfer functions, so the transfer function representation of a system is unique. For a linear time invariant system, there is only one transfer function. But you can write many state space models for the same system. And some of these models will have certain advantages, and this is used quite a lot in modern control. Well, they all represent the same system, which means the eigenvalues of the matrix A should be equal to the eigenvalues of the matrix for the transformed system, which is T times A times T inverse. And this is very easy to prove, so they're the same. However, the form of this matrix will be changing. So the numerical values of the elements will be changing. And this may bring you some nice properties. For instance, you can separate the modes of the system. You can put this matrix into a diagonal form, or sometimes it may be purely diagonal, but sometimes you can't write it in a purely diagonal form, but you write it in a form similar to that, like a Jordan form. Or sometimes certain models are known as some canonical models. You have controllable canonical form or observable canonical form. So each one of these special state space models have some advantages, and these advantages are used quite commonly in modern control. So we'll be talking about details about that later. So I'm going to stop this video, and in the next video we will continue with the review of modern control, and we will be talking about concepts like eigenvalues, eigenvectors, controllability, observability. All those important concepts will be explained in the next few videos. So I will talk to you in the next video.